Hey everybody, welcome back. So we are continue 14.5 today. So it's a part, kind of a part, not the chain rule, but idea is implicit differentiation. Okay. This one. I'm sure you guys did in the calculus 1 class. So what the mean is, if you have y equal to f of x, this is pretty much 2D dimension. Our function is about the x value. Okay? So our x is x, but y value is based on the x. Okay? So my chart is, it's a big function is f. So under the f, we have x value, and we have y value, but y is based on the x. So which means x is, it's always x. But y is in terms of the x. Does that make sense? So that's the chart, or that's the branch you should understand. The function is, it's in the xy, still x and y. But x is, it's in terms of the x, but y is in terms of the y. So how do you take the derivative about the x? Okay. So here is partial derivative f with respect to the x, right? The x, derivative x to the derivative x. The partial derivative f with respect to y, the y is based on the x, right? So y derivative x. Yeah. Where the equal to 0 coming? You have to understand why it's equal to 0, because we take the left side derivative, that's the distance. The right side is 0. If I take the 0, is always 0 no matter what. Okay? So that is our concept of the in terms of the x. Yeah, how do you make the dy dx by itself? Dy dx by itself. So I want to get the dy dx by itself. Listen. Which means I have to move this one to the right side, right? So it's going to end up the, before that, what's this? What's the dx? It's derivative about the dx, right? So x, let's take the derivative x. Okay, it's a 1, right? So this is means 1, and the partial derivative f with respect to the y. So dy dx equal to 0. So what's my doing? Let's make the dy dx by itself. So I have to move this partial derivative f with respect to x to the right side and divide by the partial derivative f with respect to the y. Does that make sense? So what we're doing is partial derivative f with respect to the y times dx dy equal, this one should be right side, right? Negative partial derivative f with respect to the x, and then let's divide by the partial derivative f with respect to the y. Sorry, partial derivative f with respect to the y. Okay, partial derivative f with respect to the y. Okay, we cancel y. So that's happening here. Can you see that? So it's a negative partial derivative f with respect to x dividing by partial derivative f with respect to the y. Yeah? So it's just like a little makes kind of a simple form, or the notation is big F partial derivative x, right? Over, it's a big F or capital F, the partial derivative y with negative sign. So this is actually, we are going to use this formula. This formula is very, very useful. Okay. Yeah, so if you kind of master how to do it, it's gonna help a lot of, like, you know, you can save a lot of time taking a derivative. Okay. Right, how do you use it? Okay, so let's practice together. Yeah. I'm gonna go to the next page. Oh, sorry guys, I forgot to take the recording. Okay. Oh, sorry, I'm doing the recording. Okay. Okay, so I'm gonna flip. Oh, sorry. Okay, so keep in mind that formula. So here's an example 7 we're gonna do. So this is a 2D dimension, so there's no z value. So make sure this is just x and y. So it's be that 2D. Okay. 2D. So what am I doing is, let's take the derivative y. Right? X cube plus y cube equals 6xy. Okay. So if you don't know the formula, so you learn from the calculus one. I just want to show you calculus one way. Okay? Then I'm going to compare the formula, how you can save the time. Okay? So if we have an x cube, let's take the derivative x, right? That's a 3x squared. Here's the y cube. Let's take the derivative, but in terms of the x, which is a 3y squared. The times, are you guys remember y prime or dy dx? Okay. The equal the right side. How do you take the derivative is, this is a product rule we can use, right? F times G, right? So 6x, take the derivative 6, and the times by the y, plus 6x leave alone, and the y derivative is a y prime, right? Y prime. You have to make the y prime by itself. So I'm going to move the 6xy prime to the left side. So 3y squared y prime minus 6xy prime. So I'm going to move to the left. The 6y, 3x squared, I'm going to move to the right. So negative 3x squared. And the y prime factored 3y squared minus 6x. 6y minus 3x squared. The last step, let's divide. So y prime 6y minus 3x squared divided by 3y squared minus 6x. Okay? Or if you want to simplify more, you can just divide by the 3, top and the bottom. I divide by the 3, which is 2y minus x squared. Divide by the 3y squared minus 2x. So that's actually our final answer. As a technique of the calculus one you guys learned. Okay. Everybody remember, right? That kind of, the integral. Then now, I want you to compare the calculus 3 technique. Okay? Multivariable technique. So what's the dy dx? What's the formula said dy dx? It's a capital F. They take the derivative about x over capital F, take the derivative y. Then what's the f? What's our function? F means it's gotta be the equal 0. Okay, so our function has to be equal 0. So my function, this one is x cube plus y cube. Then move to the left, minus 6xy equals 0. So here's our function. It's a capital F function. Okay, so x cube, y cube minus 3xy. Yeah. So what's my doing for the top numerator is, I should take the partial derivative about the x. Like focus on the x, y is a constant. So take the derivative x is 3x squared, right? But y is a constant, so just go away. Take the derivative x. So 6 is a constant, y is a constant, so it's negative 6y. Okay? So now I have to do exactly same, but I have to take the partial derivative about y. Yeah, so same thing, y cubed, x cubed is a constant, go away. Y cubed, so 3 y squared. Then take the derivative y, right? Everything constant, then negative 6. X is the constant, so y is 1. Okay? So what's the answer? dy dx equal, don't forget the negative, negative. Yeah. Capital F partial derivative x, capital F partial derivative y, which is equal negative 3x squared minus 6y over 3y squared minus 6x. Okay. So now, okay, doesn't look like same, but again, it's gonna be same. Let's divide by the 3. Okay, so let's divide by the 3, divide by the 3. So what's happening, right? So leave the negative, divide by the 3x squared minus 2y, divide by the 3y squared minus 2x. But if you put the negative back, you can see it's gonna positive 2y minus x squared. So it's the same answer. It's a definitely same answer you can have. Any questions? How you guys doing? Are you guys okay? This technique is, it's really save your time. Yeah. So you should really master that technique instead of always having a calculus 1 technique. Everybody okay? Okay, thank you for showing up, everybody. Appreciate it. Okay, thank you, Grace. All right. All right. Then what happened if I want to take the derivative, but now it's a 3D. These are 2D dimensions, right? 2D, because it's a variable x and y. Okay. So now let's try the same concept, but if it is 3D dimensions, right? If z equal in terms of the x and y, but you can make the equal 0, right? Equal 0. Because it just move to the left side, everything left side to make the equal 0. Yeah. So that means I want to make sure what's the kind of structure is I have capital F, but those are based on the x, y, z. But make sure our z value is based on the x and y. Okay, our z is based on the x and y. But x is x. X is based on the x. Y is based on the y. But z is based on the x and y. Does that make sense? That structure. Okay. You plug in the x and the y value, finding a z value. That's the 3D dimension works. So that's this picture, the construction concept. So how do you take the derivative about the x or about the y? Okay. So here is, so partial derivative f with respect to the x, right? Go ahead. The x is going to the x. So partial derivative x going to the x. Okay? Oh. Sorry. Dx is x dx, because you have only one variable happening here. Okay? The plus partial derivative y, right? Partial derivative f with respect to the y. But unfortunately, I can't have the x here. Right? If I take the derivative in terms of the x, if I don't have it, what's going to happen, right? Because I don't have an x value here underneath. Okay? But I have to keep going. This is all talking about the variable x. Then we can do exactly talking about the variable y. Okay? But right now, y value has no x. That's a concept. the partial derivative f with respect to z, the z has x, right? Z has x. So now partial derivative z with respect to the x. And make sure this is a equal 0, equal 0. That means right side is equal 0. Yeah? And now just think about the concept. What's this? What's the dx dx? What's the dy dx? This part. Just I have to figure out the first. So I have an x, and in terms of the x, I'm going to take the derivative x. Oh, I have an x equal to x. Let's take the derivative, which is 1, right? How about this one? It's a y, but there is no x value. Even I want to take the derivative about the x. There is no x means 0. Does that make sense, guys? So what's going to happen is, let's say, yeah, so partial derivative f with respect to the x times 1, right? Times 1 plus, this is a 0. So 0 times whatever is always 0. So it's going to go away here. The partial derivative f with respect to the z, times the partial derivative z with respect to x equals 0. Yeah. So I want to make the z with respect to x by itself because I'm focusing on the function z value. Let's take the derivative x. Yeah. So I want to make this is by itself. So what you have to do, move the partial derivative f with respect to x to the right side and divide by the partial derivative f with respect to z. Okay? So partial derivative z with respect to x equal, let's move it to the right. So it's a negative partial derivative f with respect to the x divided by partial derivative f with respect to the z. Yeah. So let's make the little simple form. This means a capital F. Let's take the derivative about x. This means capital F. Let's take the derivative about z. So this is again, it's a nice formula happening right here. So if we want to take the derivative z, but with respect to x is negative, it's a capital F functions, which means it's equal to 0. Yeah, that one. Equal to 0. Then let's take the derivative about x. The equal to 0. Then let's take the derivative about z. Okay? That's the reason. But this is the derivative about x. Then if you use exactly same step, what's happened? Partial derivative z with respect to the y. Because we should have the y value too, right? So if you can take the x value, we have a y value as well. So exactly same concept, it's a negative. So what's happened is partial derivative f with respect to there's no x because we are taking a derivative x. That's why it's a derivative x. Right now we have to change it to the y. Derivative y. Okay? Then partial derivative f with respect to z. So with respect to the z. So if I make the simple form, so it's a partial derivative capital F derivative about y divided by capital F derivative about z. So that's the two our partial derivative, but partial derivative formula. It's really useful if you can master this. Any questions, guys? Yeah, let's practice how to use it. So we're gonna practice. So this is our functions. Can you see? X cubed plus y cubed plus z cubed plus 6xz equal 1. You can see this is not z equal, right? If it is z equal, we practiced pretty much last week how to take the derivatives or partial derivatives. But that question, there is no way you can make the z by itself. But still I have to find out what's the partial derivative z with respect to the x, or what's the partial derivative z with respect to the y. Even there is no way we can make the z equal. So I have to use that formula. So first, I wanna make function let's make that equal 0. I need equal 0. So which means x cubed plus y cubed plus z cubed plus 6xy z minus 1 equals 0. Yeah? So this is my function, which is our equal 0. It's a capital F. Yeah? What's the partial derivative z with respect to x equal negative, okay? Capital derivative x and the derivative y. I'm going to take the first derivative x. Not too bad. Let's take the derivative about the x. It's 3x squared z cubed. Oh, sorry, this not the f. Z. Right? Y cube, y is a constant in this case. That's a go away. Z cube, also same, z is a constant, it's going to go away. Yeah? We are only focused on the x, take the derivative x. Everything else, it's a constant. So y is a constant, z is a constant. Let's take the derivative x, which is 6yz, right? The negative 1 is a constant, go away. Yeah? This is my derivative x. So I have to do next time derivative z, which means x is a constant, go away. Y is a constant. Let's take the derivative z, which is 3z squared. Let's take the derivative z, 6xy. Yeah? The z go away. Okay? Actually, z is the 1. The negative 1 go away. So that is our partial derivative. So answer is, okay, I'm going to write negative 3x squared plus 6yz divided by 3z squared plus 6xy. If you want to simplify, you can just simplify, divide by the 3. It works. If I do that, divide by the 3. X squared divided by the 3, 2yz, divide by the 3, z squared, divide by the 3, 2xy. Any questions? How are you doing, guys? So that's your final answer. Exactly, you can do the same step, partial derivative z with respect to y. I just need to find the capital F derivative about y. So just a numerator change. So easy to remember the even formula. Right? If we are looking for the derivative about y, so numerator is a derivative y, the denominator is derivative z. That's the happen. Yeah. Same thing, if you are taking a derivative about the x, numerator is a derivative x, the denominator is derivative z. Yeah. If you are looking for the last one, what's the partial derivative z with respect to y? So I need y. So I gotta take the derivative y, which is 3y squared. I don't have a y, I have a y here. So it's a 6xz. So that's it. So negative answer is 3y squared plus 6xz over derivative z, 3z squared plus 6xy. Then you can just divide by the 3, so divide by the 3. Y squared 2xz divided by z squared 2xy. Right, how are you doing, guys? So this is your final answer. Any question? Are you guys doing okay? Thank you, Cameron. Thank you, everybody. Thank you for the reaction. Thank you, Hakap. And Inet, thank you for that. Hi, can I move on the last one? So that's the topic for this section. Okay, we are pretty much doing a bunch of the partial derivative stuff, plus chain rule concept. So I'm gonna do the list. You guys remember calculus 1 when you check? We have a related rate questions. That's right. This is an alternative and faster way. That's exactly right. Yes, Ray. But I did want you to use this one all the time. This is the most easy to do if you have an implicit. Yeah. If you cannot make the z by itself, that's the way it works. But if you cannot make the x, okay, y by itself, that's the way it works. Okay? That's right. Okay, so let's move on. The related rate questions. I'm sure you guys did related rate for the calculus 1 class. So we have a 3D dimensions, which means more variables for the related rate questions. So what they're saying is radius of circular cone. Okay, let's say we have a circular cone here. Circular cone. Okay. And what's happening? Increasing the rate of the 1.5 inch per second, while height is decreasing at the rate of the 2.5 inch second. Okay. So its radius is, okay, so make sure radius is increasing at the rate of the 1.5 inch per second. But however, if radius increase, meaning is its height is decreasing. Oh, height is decreasing 2.5 inch per second. Yeah. So let's make it. So this is my R, radius R. Yeah, that's the R. That's the H. Okay. So what they're saying is, if your radius is increased, so this R is getting bigger and bigger and bigger. How far it's getting changed is, this is the dr based on the time, right? dt. So that's the rate of the how radius is changing it, which is 1.3 inch per second. But now its height is decreasing. So this 2.5 means dh dt, right? Based on the time, how height to change. But it's a decrease, so I need a negative of 2.5 inch per second. Okay? So that's the information is given. So what's my looking for? We are looking for at what's rate of the volume? How volume change of the cone changing when radius is 110 inches and the height is 136 inches. So we are looking for the volume. So our goal is volume, which is how volume change? dV dt. How volume change based on the time. That's our goal. Right? That when radius is 110 inch and the height is 136 inches. Okay? That's the information we have. Okay, so we are looking for the how volume change. It's the rate of the volume, right? So we need a formula for the volume. V equal. So it's a circular cone. What's the formula of the volume? Volume should be pi r square, which is the base, times the height, h. But it's a cone, which means we need 1/3. That makes sense? That's the formula of the volume, circular cone. So pi r square is the base times the height, and the times by the 1/3. We are looking for how volume change based on the time. Okay, so I need a structure for that. Okay. So volume is based on the R and H, right? That's my variables, R and the H. The R is also it's based on the time. So R changes time, H is also based on the time. Right? So now we are looking for partial derivative V with respect to the time t. Okay? So we are looking for partial derivative V or with respect to the time. Oh. dV dt. Okay. So I have to go to the partial derivative V, right? With respect to the R. The R going to the dr dt plus partial derivative H, partial derivative V with respect to the H, by H going to dH dt. Okay? So make sure information we have, I have to use it. What's the dr dt? Dr dt is we have 1.3. So I'm ready to plug in 1.3, right? What's the dH dt? We have negative 2.5. But I need to find what's the partial derivative V with respect to the R. So we have a V. So which is, sorry, I need more space. Partial derivative V with respect to the R. Let's take the derivative R, right? So 1/3 pi is a constant, and the R, if I take that 2R, and the H, I have to leave it. Okay? So it's be the 2/3 pi RH. The same thing, I need a partial derivative V with respect to the H. Sorry. Now take the derivative H, which is actually 1. Everything is constant. 1/3 pi R squared. Okay. Actually, that's it. That's pretty much everything we need. I just need to plug in the number. So I'm gonna start putting that all together. So partial derivative V with respect to R is this 2/3. 2/3 pi. And what's the R, right? R is when exactly 110 inches. So 110. What's the H? H is 136. The times dr dt, which is 1.3. Yeah, so that's it. The plus partial derivative V with respect to H, which is 1/3 pi R square. R is 110. So 110 square times dH dt. dH dt, it's a negative 2.5. Right? We had it. Negative 2.5. Okay? So just to finish that math, you can get the final answer. Yeah. You don't need to get the decimal number. Actually, it's going to end up the nice number. Just leave the pi. If I just do the all of the calculation, it's going to end up the 2,882 pi. That's usually. It's a volume, how change it based on the time. So it's a volume, so it's an inch cube, cubic inch per second, right? Second. How you doing, guys? Any question? Everybody okay? Okay, that's the one example for the related rate. This question is also your homework. I pick up from the homework questions. So I like to do that, you know, before you're gonna do yourself for the homework. Did you guys have a fun yesterday? So are you guys awake? I'm kind of tired this morning. So, all right, then let's move on to one more. Yeah, one more example for the related rate. So this is what you're saying is length L and the width and the height of just regular box. Okay, changing with time. So let's say I'm gonna draw the picture. Here's my box. Here's my box. What the same? Okay, we have a L, length, width, height. Okay, at a certain instant diameter, L is 8 meters. Okay, so there says L is 8 meters. The W and the H are 3 meters each. The L and the W are increasing. Okay, L and the W are increasing. How increasing? L and W are increasing at the rate of the 2 meters per inch, but H is decreasing for the 4 meters per second. Okay, so based on that information, so we can say DL based on the time is the same as DW based on the time is increased by 2 meters per second. Yeah. The DH based on the time is decreasing, which is negative. It's 4 meters per second. So boxes change based on the time. What am I looking for? At the instant of finding the rate for the following the questions change. Oh, sorry, I'm gonna write the questions. Question say A. How volume change? Yeah, that's the question. If the length and the width change 2 meters per second, so H is negative 4 meters per second. At the moment of the 8 meter and then W is 3 meter, H is 3 meter, how volume change? That's these questions. So we are looking for the volume, which is dV dt. When L is 8 meters, also W and the H are 3 meters. So that's the question. Also, can you make the kind of structure? How volume structure? How is a V of the kind of prime tree or the tree branches I want to make? The V is based on the what? Our volume is based on the L and the W and the H, right? Because V equal LWH, right? Length times width times height. The L is also based on the time. W is based on time. H is based on time. Okay, we are looking for D, V, D, T. So partial derivative V with respect to the L go to dL dt plus partial derivative V with respect to the W, the W dW dt plus partial derivative V with respect to the H times dH dt. Yeah? Everybody okay? Clear? Okay, so now you know the volume formula because we are talking about the volume. We need the formula for the volume, which is V equal, I'm sure you guys know, V equal L W H. Yeah. So let's do this. So what is partial derivative V with respect to the L? Let's take the derivative L, right? Which is 1. That is the WH. Yeah? Yeah, that's a disparator. Partial derivative V with respect to L. Then dL dt, what's the dL dt? Exactly 2 meters. So times by the 2. So now next one, partial derivative V with respect to the W. Okay, let's take the derivative W, which is LH. Then dW dt, which is times by the 2. Then partial derivative V with respect to the H, which is LW. Then dH dt, that's the update -4. Yeah. Then I just have all the number to ready to plug in. Okay, W and the H is a 3 meters, right? 3 times 3, that's a 9. So 9 times 2, 9 times 2, sorry, 9 times 2, F times H, so 24 times 2. Okay. Next one, L times W, again, 24 times -4. Yeah. Then we'll just finish the math, you can get the final answer. So 2 times 9, it's 18, and the 24 times 2, it's 48, and the subtract, this is so 96, so subtract the 96, so you should end up the -30. Just to finish the math, you can use a calculator. But this is how volume change, V. So the volume formula is cubic meter per second based on time. Any questions? How you doing, guys? This is one of the, again, homework questions. The homework has a couple more, 2 more like little questions. They are also asking is how surface area change. Okay, so you should know surface area formula. But surface area pretty much same, right? Like L times H, front and the back, W times H, left and the right, and the top and the bottom. L times W, top and the bottom. The times by the 2, that's a surface area formula. But all the structures are same steps you can do. How you doing, guys? Any questions so far? You guys okay? Can I move? This is the end of the 14.5. Okay, we did. I need to stretch. Okay, can I move on? So we are moving on the next section, 14.6. You guys okay for the copying? Yeah. Right, I'm gonna move on 14.6 today. Here, 14.6. This is again derivative 2, but it's a two different derivatives we're going to talk about. One is called direction derivatives. Okay? There's one more, it's a special vector. This affects later a lot. It's called the gradient vector. Okay. So first topic is direction derivatives. Also, by the way, please check the announcement. I put the study guide for the next week on Monday, exam 2, chapter 14. So right now, whatever we're doing, it's going to be the next exam, right? Especially these topics, directional derivatives, it's one of the topic you should really study, and the gradient vector as well. So in this section, we introduce type of the derivatives called directional derivatives. Being able to use the find of the rate of the change of the function to or more variable in any directions. Okay, so far all the derivative we did or partial derivative we did is based on the x. Don't you remember that? Or based on the y, right? Partial derivative f with respect to x, which means if you go back to a couple sections before, like here, did you understand that? That's how we did the partial derivative x, which meaning is what they're saying is y is fixed. It's a direction, it's only x is changing it. So we are kind of focusing on the only x directions. Okay, same thing, partial derivative with respect to y means direction of the y. So that's our picture, right? So this is our x directions. Okay, so only focusing on the direction is x. Let's take the derivative, which is tangent slope, right? That's our partial derivative, x means, right? If y direction, this y direction, no y directions, let's take the derivative about y, which is the only direction about y. Then let's take the derivative. Then what's happening? If I want to take the derivative, not the x, not the y, any directions. Okay, I'm going to choose a random direction here. Then can I take the derivative any direction I want? Which yes, we can. But that's what we are talking about here. Sorry. Gradient vector. Sorry, directional derivative. Then I'm gonna pick the direction whatever I want. Okay, so let's say here's can you see 3D dimensions, our curve surface. Okay, then I pick the direction right here. I want to take the derivative about that direction, not that just the x or just not y, any direction I want. Okay, so I'm gonna pick the direction right here. This one. I'm gonna pick that directions. I decided that's my directions. We called U hat. This is actually the unit vector, but I picked that direction of the unit vector. Okay, so make sure our direction is right now. Let's call the A and then B. Then it's B, the unit vector. That's my direction. So here's my curve, 3D dimensions. So I'm gonna move that direction to the 3D dimension. So I'm gonna cut in that curve. Can you see that? As a 3D, right here. Okay. So when I pick the directions, let's call this point is P dash. This point is Q dash. Yeah, I need how to see Q dash. Q dash. Dash. If I transform to the 3D dimension, that's my curve, P and Q. So what we say is, let's take the derivative about that curve. So here's my tangent. That's my tangent curve. right here. So how do you take that derivative? So it's pretty much this concept is the same. We have to take the limit no matter what. And the notation is a little picky. Okay? So this is the derivative notations. And this symbol U meaning is it's a direction. Which direction am I taking? Exactly which point of the derivative we are taking. Okay, so I want to make a little bigger. So D is my derivative and the direction of the unit vector, the function of the curve exactly at that point. So point is we call x naught, y naught. So that's the formula, or that's the notation we use. Yeah. So first, exactly which point you want to take the derivative, and which direction you want to take the derivative. So at that point here, and the unit vector at that. So how do you do that? So I know it's a limit because its derivative is always the limit for the calculus 1 definition, right? F of the sum about the h minus original divided by the h. So that concept doesn't change. But again, we're not going to use the limit all the time. That's why we have a nice formula to take all the derivatives. So here is the formula we're going to use for the directional derivative. F has directional derivative in direction any unit vector. Okay, so you gotta be careful. Only direction you can take. You can take the any direction, but has to be the unit vector. Otherwise, that formula doesn't work. It's gotta be the unit vector. Then it's harder to see, but how do you take the derivative is? So partial derivative x, okay? Partial derivative f with respect to x times a. Where's the a? A is coming from the direction. Okay? Plus partial derivative f, the partial derivative f with respect to y times direction b. Okay? This is our directional derivative formula. Okay? Make sure our a and then b are directional. This a and b are our direction from the unit vector. Direction vector. Okay. Okay, then let's practice how to use it. Okay, so we can practice it. It's not hard to do it. Okay? So look at that. Find the directional derivative of the derivative of, U is hard to say, but function f. If our function f is that one, I'm gonna just rewrite it. So you guys hard to see like this. Function is x cubed minus 3xy plus 4y squared. Yeah? So that's my function. Then where's the direction, right? Because it's a directional derivative, I need directions. What's the direction say? Direction is unit vector given by the angle theta pi over 6. At that point, 1, 2. Okay. So if you do the directional derivative, okay, so let me make sure you guys understand this. So what they're saying is, I have an x and y. First, think about the directions. What's my direction? U is, it's a pi over 6. The angle, pi over 6. So that's my directions. It's gonna be the unit vector, U. So how do you find the unit vector direction pi over 6, AB? Otherwise, I cannot find this A and B. How you do that? You guys remember? Okay, look at this picture. Let's say I'm looking for the unit vector direction pi or direction angle theta. How you do that is unit vector. This actually is a right triangle, right? Right triangle. So I just need to know whether directions or what's the ordered pair A and B. Especially this is the right triangles. So we can use a trick, angle theta. Don't you remember that Sokato? Right? If we have a right triangle, this is the angle theta. So this means this is the x value as cosine, right? The y value as a sine. So this ordered pair at that point is x is cosine, right? Y is a sine. So make sure you know our y value is sine, x value is cosine. It's a right triangle unit vector. So you can just pretty much use Sokato concept. So which means if I have a pi over 6, right? Pi over 6. So what's my x value? What's my y value? Which is a cosine pi over 6 and sine pi over 6. So I can say, so what's the cosine pi over 6? That should be our A. That's my A, right? Ordered pair x. So this one, that's a B, is sine pi over 6. Yeah. So cosine pi over 6, what's the unit circle? Everybody wake up, what's the cosine pi over 6? Cosine pi over 6, the radical 3 over 2, is that right? The sine pi over 6 is the 1/2. Yeah. So that's my A and B. Okay. So it's not too bad. Okay, so now my unit vector direction is radical 3 over 2 and then 1/2. Yeah, that's my direction. So I got the direction ready, but I need a partial derivative x and a partial derivative y. So what is a partial derivative x? If I have a function x. So let's take the derivative x. So 3x squared derivative x minus 3y. Yeah? There's no x. So make sure at 1, 2, right? Yeah, at 1, 2. So make sure we have a specific point of taking a derivative. So it's a 1, 2. So I have to plug in the 1, the 2. So partial derivative x, plug in the 1, 2. So what you got? Same, partial derivative y. Let's take the derivative y. So if I take the derivative y, so negative 3x, derivative y, 8y at 1, 2. The partial derivative y, so put in the 1, 2. What I got? Okay, if I plug in the 1, which is 3, and subtract the 6, the negative 3. Negative 3. If I plug in the 1, sorry, camera froze right now. Okay. Let me reset the camera. Sorry, guys. Can you guys hear my outside of my noise? The next door is major construction going on the outside. So if you hear some noise, I apologize for that. I just start really making a noise right now. Okay, so now my camera back. Thank you, Nat. Okay, so hopefully, it's not distracting you guys for the hearing what's my saying. All right, let's plug in the 1, the 2. So plug in the 1, negative 3, and plug in the 2, 18. So negative 3 plus, 16. which is 13. Okay, so now here's the notations. So we are taking a directional derivative of the direction u of the function at the point 1, 2. Okay? So what's the formula say is partial derivative x times a. This is my a and the b. Okay? So it's negative 3 times a, radical 3 over 2, the plus 13 partial derivative, 13 times 1/2. Okay. So what's the answer? Okay. I don't think we cannot simplify. So its denominator is 2. So negative 3 radical 3. Then this is a 2 over 13 plus 1 13. Okay. Well, that's it. This is your final answer. There's nothing to simplify. So this is our directional derivative. Any question? You guys okay here? Okay. Yeah, let's move on. Couple more page and then I can just go back. There's one more vector. It's how related the directional derivative. It's called the gradient vector. Yeah. So we're gonna talk about the gradient vector. Gradient vector you're gonna hear a lot okay, from now on. So what's the gradient vector? It's a pretty easy. Gradient vector is it's a vector. What kind of vector? It's gonna be the two variables x and y. If function has two variables, or could be 3. That's fine. The gradient of the f. Also, the notation we use is a triangle opposite. We call del. Okay. It's called del. Okay. So it's called it's a del f, which means it's a gradient vector. Okay. Gradient of f, a del f. You know computer for the del, right? That's a triangle opposite, the del. Yeah. Right? They defined. So what's the gradient vector or del f is just a partial derivative x. Okay, or partial derivative y, and it's just a vector notation. That's it. That's called the gradient vector. It's nothing changed, nothing fancy. What we learn from the pretty much partial derivative x and the partial derivative y makes ij vector notations. That's it. Okay. It just they have a fancy name. That's it. Okay, so let's take example too quickly. So we have a function. Function f of x and y is a sine x plus e to the x and y. And we are talking about, let's find the gradient vector. Okay? So I'm gonna do pretty much what they're saying is, still partial derivatives. Let's take the partial derivative x. So what's the partial derivative x? Sine x, it's a cosine x, right? Let's take the derivative x, but e to the xy and the e to the xy. But I need to take the derivative x, which means it's times by the y. That's it. The same thing, let's take the partial derivative y, but sine x is 0 because there is no y. So take the derivative about y, which is e to the xy. Then take the derivative y, it's beta x, right? So what's the gradient vector? It's just a notation, or del f is partial derivative x, the partial derivative y of the vector notation. So you can say cosine x plus y e to the xy and then x e to the xy. That's my y. So that's it. That's your answer. Just nothing change. Just let's take the derivative each time x and y. Then let's make the ij or like vector notation. Okay. Well, how this one related? Okay. So look at the gradient vector formula one more time. This one. I want to take a look at the gradient vector or directional derivative formula. Okay, I'm going to copy this one. Okay. Here's a note. Okay. So our directional derivative of the direction u, the function x and y, okay. And what's the direction is AB, right? AB. So what's they say? Partial derivative x times a plus partial derivative y times b. So that's my formula set exactly the back page. A partial derivative x times a plus partial derivative y times b. But this one, if I really pay attention carefully, but this is a partial derivative x and the partial derivative y of the vector dot product of the AB. Don't you? Well, that's a dot product formula. Is it, guys? Well, that is dot product. Okay? Because f times a, the f times b, and you add it. Oh, that's a dot product. So if you rewrite that directional derivative formula for the kind of simple way, it's be, what's my doing? Gradient vector. Dot product of our direction of the unit vector. Okay. So here's I'm gonna rewrite. Okay. So directional derivative, direction u, function x and y is del f, which is a gradient vector, dot our unit vector of the direction. Any questions, guys? Yeah. Maybe right. Vector, and this is a unit vector dot product. Okay. So this makes much easier to understand what's the directional derivative. Okay. So we need a gradient vector. Then we need a unit vector of that which direction we are taking the derivative. Then do the dot product. So let's the examples quickly. Any questions, guys? Are you guys okay so far? Find the directional derivative of the function. Okay. So here's my function. At the point 2, -1, and what's my directions? Direction is 2i plus 5j. Okay. So first we have a function f. X and y. Function is x squared y cubed minus 4y. Okay. And we are going to talk about exactly the specific point 2, -1 later. The first, what we need, let's find the gradient vector. Okay, I'm gonna find the gradient vector, which is partial derivative x, partial derivative y. Okay, so let's do this. Del f. Let's take the derivative x, which is 2x y cubed. There's no x, right? Let's take the derivative y, which is 3. Okay, x leave alone, y squared, and the derivative y -4. Okay. The specific at the point to negative 1. So I'm gonna do, so what's the 2 negative 1? Gradient vector exactly 2 negative 1. Okay. So plug in the 2, then plug in the negative 1, right? So 2 times 2 and a negative 1 cube, that's a negative 4, right? Next one, 2 times 2, 4, 12, and the negative 1 square is a positive 12, the minus 4. So that's 8. Very good. Okay, so here is my gradient vector, exactly specific point at 2, negative 1. Okay, we are ready for the gradient vector. Next, where the directions? Okay, so they say direction is the vector. Direction vector is 2 and 5. But you gotta be careful, right? It is a unit vector or not? If you have a direction 2 and 5, it is direction. It's a unit vector. If it is a unit vector, should be magnitude has to be 1, right? If I measure that magnitude, 2 times 2, 4. 5 times 5, 25. The square root. That's a radical 29. That's clearly not the unit vector because the 29. The length is 29. So I want to change unit vector u. How do you do it? You know, if you want to make the unit vector, I have to divide by the radical 29. So it's be that 2 over radical 29, 5 over radical 29. So now, almost done. So we are looking for directional derivative direction u function of exactly 2, negative 1. Okay. So gradient vector dot product of unit vector. So we're gonna do it. So this and this dot product. That's it. That's all we're doing. Okay, dot product is a times like negative 4 times 2 radical 29. Then adding times 8 times 5 radical 29. Okay, so what's I got? Negative 8 plus 40. So negative 8 plus 40, so which is 32, is that right? Over the 29. So here's your final answer. Hey guys, how you doing? Yeah, almost. Yeah, thank you, Haka. Everybody okay? Any questions so far? I mean, calculus 3 has a lots of formulas, lots of formula coming up even from now on. Okay, so whenever you learn something new, put the nice kind of a formula paper, organize your information so you're not gonna lose what you're learning, especially exam coming up soon, you know, the next Monday. All right, so let's move on the next page. Okay, so it's couple more page we are done. Okay. So if we have 3 variables, can I do the directional derivatives? Yes, you can. It's a pretty much the same concept. No matter how many variables you have, its formula doesn't change. So it's a function of the 3 variables. Directional derivative, if we have 3 variables, and the direction pretty much you need, like instead of AB, let's say ABC, you know, 3D dimensions. So pretty much same. So what am I doing is, again, del or gradient vector dot product of the unit vector. So doesn't matter how many variables you have, just always gradient vector dot product of whatever the unit or direction you are taking. But it's gonna be the unit vector of direction. Okay. Here is the gradient vector. So I have a f, x, y, z gradient vector because we are talking about the 3 variable, right? Gradient vector. Again, doesn't matter how many variables you have. You just, as long as you have a gradient vector and then you have a unit vector of the directions, you can make the directional derivative everywhere. Right. Yeah, let's go to the next page. Hopefully we finish this page and let's see I can get this last page today or not. Okay, so keep in mind this one. Example 4. So what they're saying is, I have a function. This function is x, y, z, 3 elements, 3 variables, right? X sine y, z. Find the gradient vector of the f. Okay, first, what we're doing is, I have a function. X, y, z, and x sine y, z. So we are doing question A. So what is gradient vector f? Which means I need a partial derivative x, partial derivative y, partial derivative z, because it's 3 variables. So we're gonna do, let's start partial derivative x. Okay, only one x. It's a 1. Okay, so sine yz. Next one, partial derivative y. Okay, x a cosine. X is constant. I can't touch it. But sine becomes the cosine. Right? Cosine yz. And the inside has a chain rule for the about y. So it's be the z. Right? Z. Yeah. The same thing. I have to take a derivative about the z. So x is constant. Sines become the cosine yz times, let's take the derivative z, which means a y. Yeah. So here's my gradient vector. Here's my gradient vector. I got that. The question B. Find the directional derivative of exactly at the point 1, 3, 0. Where's the directions? Oh, here's my directions. So our direction is, okay, I need to ijk 1, 2, -1. Yeah. First, I'm going to plug in the 1, 3, 0 to specific point for the gradient vector. So our gradient vector at 1, 3, 0. Yeah. So sine, if I plug in the z equals 0, sine 0 is 0. So I don't need to worry about it. Okay. X is 1. Cosine is 3 times z equals 0. Oh, actually, oh, and z is a 0. So again, it's a 0, right? Again, because z makes equal 0, everything goes 0. So it's easy. Okay, so now x is 1. Cosine yz, which is a cosine 0. Cosine 0 is 1, right? The y equals 3. So 1 times 3, which is 3. 3. So here's my gradient vector, specific 1, 3, 0 point. Okay, so how about what's my direction? Right? I'm going to start question B. Okay. So direction is this one. But it is a unit vector. It's gotta be the unit vector, otherwise it doesn't work. So let's make sure it's a unit vector or not. What's the magnitude? 1 squares 1, 2 squares 4, the negative 1 is 1. It's a radical 6. What's my unit vector is 1 over radical 6, 2 over radical 6, the negative 1 over radical 6. Okay? So here's my unit vector, the direction. Okay, so finally, directional derivative of our direction u, the function of 1, 3, 0. So make sure del f dot the product of unit vector. Okay, so I'm gonna do the just dot product. Actually, that dot product is makes easy because it's a 0, right? 0 times whatever is 0. Plus again, 0 times whatever is 0. And the last one, 3 times, last one, 3 times negative 1 over radical 6. Okay, negative 3 radical 6. Okay, so here's the final answer. Any questions, guys? Are you guys good? Hopefully you guys going okay. Okay, sorry, I want to finish one more topic right here. Today. Any questions so far? Okay, so one of the topics for the exam, it's a gradient vector and the directional derivative. And here, we'll make sure, please review before the exam that topics. That's definitely you'll be asked. Here. Maximizing a directional derivative. So, as I mentioned, which directions you can take is, I say you can take any direction you want because we learned the directional derivatives. So you can choose any directions. But again, based on the directions, directional derivative will change. So what's the topic is, I want to make the maximize this directional derivative, which means which directions should I take? Because function, I cannot change it. Function normally is giving the questions, right? But directions, because we can choose any direction I want. So choose the directions makes maximizing that directional derivatives. So that's this topic talking about, maximizing the directional derivative. So in which these direction does the function f changing fastest, and what is the maximum rate of the change? So pretty much you have to think about in which directions makes function change fastest. Meaning is, make sure this directional derivative makes fastest, or maximum rate of change, same thing. Maximum rate of change meaning that one too. It's rate of change that derivative means, right? It's a related to rate. So I want to make the maximize the rate of change. Okay. So how do you make the maximize this directional derivative? Which direction should I take? Okay. The gradient vector of our unit vector. So they are talking about in which direction should I take? Which of that direction is best? Yeah. Makes maximize or makes the fastest for the changing of f. So here's a theorem we have. Suppose f is a differential. Okay, we are able to take a derivative or 2 or 3 variables. Maximize value of the directional derivative. That one is what it says, magnitude of this gradient vector, and it's called when our this direction is what is it? Same direction as the gradient vector. Okay, wait a minute. Okay, so just think about it. Okay, so what they're saying is, if you take the direction is the same direction as the gradient vector, is the best to make the maximizer. Why is that? So if you take these two vectors has the same directions, makes this different, this directional derivative makes max, that is it. Makes maximize the value. why is that? So I'm gonna make a quick note here. Quick note. Okay, so directional derivative formula said del F dot product of whatever the direction, right? But if you go back to chapter 12, what's the dot product formula said? Dot product is magnitude of the each vector times angle between two vectors. That's the original formula for the dot product. Okay? Magnitude of each vector times, not the dot product, this is times angle between two vectors. That's the dot product formula. This is a dot product, right? Dot product. You know this is a unit vector u. So if you take the magnitude normal, it's a 1. So it's gonna end up well, magnitude of gradient vector times angle cosine scalar. So wait a minute. Cosine scalar is normal between -1 to 1 because the trigonometric, right? The unit circle. So cosine is between -1 to 1. But if you want to make the maximize value, make the max. To make a maximum value, max value, what's the value I have to take? Is 1, right? Oh, it's gotta be the 1, otherwise it's just a fraction or makes it smaller. Oh, so I have to take the 1. But think about it, if cosine is 1, right? If cosine equal 1, so what's the angle is that? What's the angle have to take? If it is cosine equal 1, meaning is it's gotta be 0 degree, right? 0 angle. That means this two vector has 0 angle between. So our vector f or gradient vector f and our unit vector is its angle is 0 angle, which means gradient vector f and our unit vector it's the same directions because that's a 0 angle means. There's no angle between. So did you understand what that means, right? So that means, so that's why unit vector is the same direction as the gradient vector. Okay, does that make sense? So that's what I say. Unit vector and gradient vector has same directions. That same direction. Does that make sense? So, but if cosine equal 1, which means the same direction, what's end up? It's gonna be, we end up the gradient vector of the magnitude. So our directional derivative, it's gonna be the magnitude of the gradient vector. That's happening. This is it makes maximum value is, see that? It's a gradient vector of magnitude. So this is our maximum value. Yeah, see that? Maximum value is the magnitude of the gradient vector with the direction. Direction is the same direction of the gradient vector and unit vector. All right, then let's finish the example 5. Yeah, I will stop today. Okay, so let's get the example 5 today. So question, any questions so far? Okay, this concept, please keep in mind because that's definitely the next exam you'll be asked. Okay? So here's my big function f. F is x e to the y find the rate of the change of the f at the point 2, 0. Then this one has a direction is given. Right now, you're not going to choose a direction. Direction is given. Direction is, well, it's a PQ. Okay. From the PQ. Okay, so here's my direction. It's vector PQ. So how do you find the vector PQ? Is you go backward, like Q minus P. So Q is this one, like 1/2. So 1/2 P is this one, not 2. So 1/2 minus 2. What's the 1/2 minus 2? Which is negative 3/2. 3/2. Then Q2 minus 0. Right? Y value 2 minus 0. So that is my directions. Okay. At least I know I have a directions for the question A. So I'm gonna write the question A here. Okay. So we are looking for what is directional, finding the rate of the change of f at the point of the direction. We are pretty much looking for directional derivative of the function f at the point 2, 0. Okay. So that means, so rate of the change means the directional derivative of that directions. So now gradient vector f dot product of our unit vector directions, because I have a direction right now. Okay. So first, let's find the gradient vector. So what's the gradient vector in this case? Okay, look at the x. Take the derivative x, right? Which is e to the y. Take the derivative y, x a constant, so x, e to the y, then at 2, 0. So I have to plug in 2, 0. So e to the 0 power is 1, right? X is 2. Again, e to the 0 power is 1. X is 2. Okay? So this is my gradient vector at 2, 0. Okay, so now let's think about the directions. Directions, we just find that. But that's not the unit vector. I gotta get the unit vector. Okay, so what's the magnitude of the PQ? I need that. If I take the magnitude of this one, the square of the square root. Right? Square is 9/2. The 0 is 0 square. But if I take it, that's 3/2. So what is my, oh, sorry, my bad. That's not 0, right? 2 minus 0 is 2. Sorry, that's my bad. That's 2. Sorry, I gotta fix it. So 9 plus 4. Sorry, guys. Please fix it. So this, our PQ is, okay, common denominator is 8. 8 plus 9, but the 25? 25 over, that's a 4. If I square it's a 4, right? 25 over 4 over the square root. That's a 5/2. Yeah? Yeah, 5/2. So now, okay, pretty much we are ready. So gradient vector. Oh, yeah, our unit vector. So what's the unit vector is I gotta make the unit vector. So I have to divide by the 5/2. Okay? So negative 3/2 divided by the 5/2. So what's that? Negative 3/2 divided by the 5/2. So nicely 2 cancelling out, so which is negative 3/5, right? Then 2 divided by the 5/2. So what's the 2 divided by 5/2? So I just want to do the little math. It's be the 4/5. Okay, reciprocal you take, right? Reciprocal you gotta take it. So here's my unit vector. So finally, what's our directional derivative of the direction u, the function of 2, 0. So I gotta do the dot product. Right? Negative 3/5 times 1, negative 3/5. 4/5 times 2, right? Which is 8/5. Ooh, actually, it's a nice 5/5. It's a 1. Yeah. Any questions? That's the question A. Question A is the directions given. So I can choose the directions. But question B, so look at the question B. In what direction does function f has a maximum rate of the, so they say exactly, I want to find the max rate of the change. And what is this maximum rate of the change? So let's find the direction first. Okay? In what direction is great? Is function, I cannot change. The function, I cannot change. To make sure. And even the point, I cannot change. Only I can choose is which direction is great. Which direction makes max. As I mentioned, right? What's that? If you want to make the maximize, direction has to be same direction as the gradient vector. Oh, same direction as the gradient vector. This one. I have to choose that direction. Okay? So I want to say if this and our unit vector are same direction, then we can say maximum value. That makes sense? So what's my directions? That's the directions, 1, 2. Because this is a vector. Vector is the directions. The answer is what direction should I choose? It's a 1, 2. That's my directions. So direction is, it's a 1, 2. That's the choosing. Then what's the maximum value? What is the maximum rate of the change? What means, what's the maximum value? Don't you know that? Maximum value is absolute value or magnitude of the gradient vector. So that is my maximum value, which is I have to take the absolute value, well, magnitude. So 1 square is 1, 2 square is 4. So answer is 5, square root of the 5. Square root of the 5. Does that make sense, you guys? They're clearly bigger than 1 because that makes maximum. So I cannot go more than radical 5. That's because that's the maximum value we can make. Any direction you choose. How are you doing, guys? Everybody okay? Any questions? Hopefully you good. Okay, I will stop.